Welcome back to this lecture series on concurrency state models and design patterns. This is the final one of the regular lectures in this series. And next week we'll have a surprise guest lecture. Today we're going to be looking at architectural styles for concurrency. Up until now we've focused more on microarchitectures, so design patterns are at a relatively local and small scale of concern, whereas architectural styles cut across the entire application. First, we'll have a quick look at what we actually mean by software architecture, and in particular what software architecture means for concurrency. We'll see that one of the most basic patterns in architectural styles for concurrency is the three-layered application architecture, which distinguishes between where concurrency occurs and where synchronization occurs in these layers. And then we'll have a look at a particularly important class of architectural styles, namely flow architectures, because many kinds of architectural styles for concurrency exploit the fact that work can be split up into a data flow, which is processed by multiple workers. And finally, we'll have a look at an interesting class of applications known as blackboard architectures, or also known as coordination frameworks or coordination media. And we'll look at a classical example of this called Lynda and an implementation in Java called Java Spaces. There are numerous sources that I'm using for the lecture today. First is the classic book by Mary Shaw and Dave Garland called Software Architecture, dating from 1996. It's the first book that really tries to present software architecture from a bit more formal perspective, in terms of splitting an architecture into components and connectors, how these components interact with each other. Another important source dating from the same time is the book by Frank Bushman and colleagues. This came out shortly after the Design Patterns book, and Bushman and his colleagues were focusing on design patterns more at the architectural level. Of course, I'm also referring to Doug Lee's book on concurrent programming in Java. He also has quite a bit to say, particularly about data flow architectures. And finally, I'm referring to the classic paper and subsequent book by Carrie-Aaron Galanter on Lynda, on how to write parallel programs using Lynda. But first, let's have a quick look at what exactly a software architecture is. So Shaw and Garland define software architecture as a way of defining a software system in terms of computational components and interactions amongst these components. And these interactions can be described in terms of connector. So how are these components allowed to communicate with each other? How are they constrained to communicate? They also speak in terms of architectural styles. Just like we speak of architectural styles for buildings, we can think of architectural styles for software. Whereas Bushman and colleagues would talk about architectural patterns, we can also talk about styles. So these are the classical or stereotypical ways in which we organize software systems from a concurrency perspective. Classical example is client-server architecture, and refinements of those could be fat client or thin client architecture. So they say where functionality occurs in the system, does it occur, what happens on the client side, what happens on the server side. And if it's a fat client or thin client, it has implications about what kinds of functionality tends to be more on the client side and what tends to be on the server side. Shaw and Garland go on to say that an architectural style can be characterized across four different kinds of properties. First of all, an architectural style defines a vocabulary of design elements. So, for example, with a client-server architecture, you talk about the client and the server, and these terms have particular meanings. And a thin client or a fat client also has a particular meaning. Once you know this vocabulary, then you can talk about these styles at a higher level of abstraction. We also talk, for example, in the data flow architecture about pipes and filters, sources and sink, or in a MapReduce architecture, we talk about the mapping and reducing functions. We also have a set of configuration rules that constrain the compositions. So, for example, pipes and filters must alternate in a linear sequence. Or if we have a layered architecture, communication goes down to the API of the level below, but not to the API above. So you have constraint about how components are composed and how they are allowed to communicate. Next, there's a semantic interpretation. So what does it mean for components to be connected to each other? In a pipes and filters architecture, for example, each filter reads bytes from its input stream and writes bytes to its output stream. In a client-server architecture, it's the client who sends a request to the server and the server sends a response back. So there's a particular payload. So there's implications about what's going in what direction and what it means to be connected. And finally, and fourth, very important, why is an architecture there? Architecture gives you particular properties that are of interest, or one can also speak about analyses that can be performed. So for a pipes and filters data flow architecture, if the filters are well behaved, that is, they don't suddenly stop communicating, then no deadlock can occur and all the filters can progress in tandem. If I have a fat client architecture, then that also has some implications. So with the fat client, a lot more activity is happening on the client side, so that improves latency and means that only requests that must be performed on the server are actually sent through the network and back, whereas just GUI interactions are happening on the client side. With a thin client architecture, you have different properties. With a thin client architecture, you have very little code that has to be loaded in the client side, so that happens very fast. However, for any kind of interaction, there's a latency to go all the way to the server and back. So these are the analyses or the properties that you get from your architecture. And this is why you apply a particular architectural style. What does it give you? Okay, now let's have a look at a particular kind of architectural style that's very important. We've actually more or less been adhering to it up until now without making a big point of it, and that's the classical three-layered application architecture. Recall from our very first lecture that there are two essentially different ways of communicating amongst processes and concurrent applications. Either you can have an underlying model of shared variables, so that processes P1, P2, and P3 here don't communicate directly, but indirectly through shared resources. So these are the shared variables X, Y, and Z. And in order for them to communicate, you need some kind of synchronization mechanisms. So every access to a shared variable happens within a critical section and must be somehow controlled, typically pessimistically, but possibly with an optimistic synchronization policy. A very different approach, or a complementary approach, is one based on message passing. Here we have no shared variables, but instead processes P1, P2, and P3 directly send messages to one another. This communication may be synchronous or asynchronous, it may be buffered, it may have fixed length buffers, or it may be fully uncontrolled. So there are different ways of realizing message passing. These different styles are complementary, but they can also be implemented each in terms of the other. For example, message passing can easily be simulated or modeled by associating message queues to each process. Now the message queues are the shared resources, and each process is either consuming messages in the queue or it needs to put a message in a queue. So a critical section is needed anytime one accesses a queue, whether one adds something to it or is reading something from the queue. So that means that message passing can be translated into shared resources. It's also possible in another way to simulate shared resources by message passing. For example, by taking a process and having it model the behavior of a shared resource. Now, the classical way of organizing processes and resources in a shared variable world is to split the world into 3 separate layers. At the top layer, we have our active objects, or our processes. At a layer below that are the synchronized shared resources. And at a lower level, we may have some objects which behave as owned resources. Recall that we want to avoid so-called nested monitor problems. By splitting the world into these 3 separate layers, we can guarantee that we don't have a synchronized object that's being accessed from another synchronized object. Instead, what you try to do, if there are objects that need to somehow be shared, we have a notion of ownership. This is the ownership pattern that we saw some weeks ago. And then these unsynchronized objects can, by some protocol, be passed from one synchronized object to another. As a consequence, you avoid nested monitor problems by restricting the current concurrency to just the middle layer. Now let's have a look at the role of data flow in concurrent architectures. So lots of synchronization problems can be avoided by arranging things so that information flows in one direction, that is from sources to filters to sinks. This is a so-called flow architecture, data flow. Now there are lots of different versions of flow architectures, lots of variants. One of the simplest is that of Unix pipes and filters. In a pipes and filters chain, processes, so Unix processes, are connected to each other in a linear sequence. And a pipes and filters chain can even be scripted from a shell language. In process control systems, we have lots of different processes which are controlling hardware devices and sensors, for example, in a factory. And here, what flows are the events which are picked up by sensors and processed and generate new events, as these are absorbed and interpreted by various devices. In such a system, you don't have a linear data flow chain like you have in a Unix pipes and filters chain, but you have a much more complex kind of data flow. And a third example is that of workflow systems. So in electronic office systems, office information systems, we simulate office documents as electronic documents that can flow through various kinds of workflow procedures. Coming back to Unix pipes, what's actually very cool about Unix pipes is that the whole synchronization infrastructure is managed for you almost for free by the operating system. Here we see a simple shell script which is combining a variety of different Unix commands. So what this script does is it's going to take a file and send its output to the output stream. So this is presumably a text file that cat is reading. Cat stands for concatenate. Its main purpose is to concatenate a bunch of files together. But by simply taking one argument, it will read that file and spit its output to the output stream. Now we see a series of pipes, shown here in the syntax of an OR bar in this shell script, and the output of the file is sent to a second command called tr. So by running this script, a process is created for the cat command, one for the tr command, one for the sort command, for unique for the other sort command, and finally for the more command. So we actually have 6 processes that are created, and they're going to be connected by these pipes. And the pipes are essentially just bounded buffers offered by or provided by the underlying operating system. So you have a bunch of processes connected by these bounded buffers. So cat is going to send all of its bytes, all of the characters in its file to tr. What does tr do? tr has a bunch of arguments here, and basically what it's doing is it's going to take all the alphabetic characters and turn them into new lines. So it's going to do a translation. The effect of this is going to take our text file, and every word in the file is now going to be appearing on a separate line. Passing this through the sort command will sort all the words, and the unique command with the -c option will actually count all of the occurrences of each word. Since the words are sorted, if I see the same word multiple times, in the output now, instead of occurring 5 times, it will appear simply prefixed by the number 5. Now we take the result and sort it in reverse numerical order. So this is a different application of sort. And now we have all of the words in the file prefixed by the number of occurrences and sorted in reverse numerical order. And now if we pipe that through more, then we'll see the result on the screen. Now with Unix pipes, there are some constraints. So there's an architectural style. So we have the vocabulary of pipes and filters and sources and sinks. And we have some constraints. So every process should read from its standard output and write to its standard from its standard input and write to its standard output. But what it should never do is stop reading until it gets, so it should always read until it gets to the end of the file. If it stops reading at some point, then this leads to what's known as a broken pipe. So there are constraints in any architecture that say for the components to be connected, they have to obey the rules. So the rules will differ for every architecture. In a pipes and filters architecture, one of the rules is that you shouldn't stop reading until you get to the end of your input. As a consequence, if you follow the rules, then what you get as payoff is that you can create these pipes and filters chains, and all of the hard concurrency work is done for you almost for free. So the processes are created and scheduled by the operating system, and the synchronization is handled implicitly by the help of these bounded buffers. Generalizing this, in any kind of data flow architecture, you have different flow stages. So every flow stage is either a producer or a consumer, or both. In a Unix pipes and filters chain, you just have sources and sinks and filters. But there may be more complicated data flows than simple chains. So for example, we can have a splitter, which is a multiplexer, so it has multiple successors. For example, a multicaster will clone the results to multiple consumers, and a router, on the other hand, will take its inputs and send each of the inputs, distribute them to different possible consumers. So there are different ways of splitting. Mergers or demultiplexers have multiple predecessors, and again, there are different variants of them. So a collector will interleave the inputs into a single consumer, whereas a combiner takes all of these inputs and processes them, takes multiple inputs and produces a single result in the end. And then a conduit has both multiple predecessors and consumers. So here we see that the vocabulary of this architectural style is being enriched when we go beyond the simple linear kind of data flows. Now the flow policies, so recall that for an architectural style there has to be an interpretation. So what does it mean to connect things? So connecting things can also be done in different ways in data flow architectures. So a flow can be pull-based or push-based or a mixture. If it's pull-based, then the consumer pulls the results from the producers. And if it's push-based, then the producer pushes the results to the consumers. And then the buffers could be put-only buffers. They connect push-based stages, or take-only buffers, which could connect pull-based stages, and so on. So you can have different kinds of approaches. So here we see a producer that's putting stuff into a buffer and a consumer that's taking things from that buffer. There's a whole bunch of other issues that you have to consider. So if the buffers are unbounded, That's attractive from some point of view, but you will have the problem that if the producers are faster than the consumers, then they may get ahead of the consumers. And if the buffers are unbounded, then eventually they may exhaust all the available memory. So that's a problem. That's why the buffers in pipes and filters chains in Unix are always of a limited length. So for producers producing too fast in a Unix pipes and filters chain, at some point it's going to try and write, but it can't. So it will block. This is similar, think back to our Java threads. If a Java thread is trying to write and it cannot because it's blocked in I/O, it temporarily becomes unrunnable. Similarly, a Unix process is trying to write and cannot, will go to sleep until it's able to write. Another issue is whether you have what's the bound on the number of threads. Clearly with the Unix pipes and filters chain, there's a fixed enumerated list of commands that get executed, and you get one process for every command. So they're strictly limited. However, if you're building a data flow within Java or your favorite programming language, then you may have, if you're creating threads manually in the code, then there may be no limit to the number of threads that you can create. Recall, of course, that there is in Java, for example, in the JUC library, the possibility of not just creating threads, but of using a pre-existing pool of threads. Bounded buffers, of course, are an alternative to unbounded buffers, as we've seen in Unix pipes and filters. But the curious thing is they tend to always either be full or always empty. So if a producer is faster than the consumer, then the buffer is always going to be full. And every time it gets emptied a little bit, the producer will produce some more. Or if the consumer is faster, then it's going to always be empty. The moment a producer puts something in the queue, it'll immediately get gobbled up by the consumer. So having very long buffers is not going to change that situation at all. So it's only if producers and consumers are more or less at the same speed that the buffers won't be always either full or empty. And as I already mentioned, an alternative to having unbounded threads is to have bounded thread pools. They can be a little bit harder to manage manually, but by using pre-existing libraries like the JUC, all that these management issues can be handled for you without any manual control. Let's have a look at a bit of a toy example. So we're going to see how we can implement a prime number sieve using active objects in a flow architecture. In this example, prime numbers are going to be agents or active objects that reject non-primes and pass on candidate primes onto the next element in the flow. Or alternatively, when they detect that there's a new prime number, then they will create a new active prime number in the chain. So in this scenario, we start with two active objects. One is test for prime, which generates integers to be tested for whether they're prime numbers, and with one prime number, one active object, a prime filter, which is initialized with the value 2. So it's a prime number 2, and it will perform tests for divisibility by 2. Active prime 2 asks for test for prime for a number to test. It gets a number 3. It sees that the number 3 is not divisible by 2, and then it tests if 3 is less than its square, or 4. 3 is less than 4, so it says, oh, I found a prime number. So now what it does is it creates a new prime number at the end of the chain of prime numbers, and that prime number will immediately start acting. So it will immediately say, hey, active prime 2, who I'm connected to, can you give me a number to test? Well, for the moment, there's nothing to test, so active prime 3 will go to sleep for a bit, waiting. Active prime 2 asks test for prime 2 for a new number, gets the number 4, says, oh no, 4 is divisible by 2. I'll just throw that away. Give me another number. So it gets the number 5, says, oh, Number 5, it's not divisible by 2. Is it bigger than 4? Oh, yes, it is. Maybe it's prime, maybe it isn't. I don't know. I'll pass it on to the next prime in the series. Active prime 3 now gets it. Says, oh, I got a number. Is it divisible by 3? No, it isn't. Interesting. Is it less than my square, 9? Oh, yeah, it is. Oh, so 5 is less than 9. It must be a prime number. So it says, I'll create a new active prime connected to the end of the chain, so connected to me. And active prime 5 immediately says, hey, do you have a number for me to test? Active prime says, not yet. Why don't you just wait? And active prime goes back and says, hey, active prime 2, got another number for me to test? Well, it doesn't yet. In the meantime, active prime 2 has asked for the number 6, thrown it away, got the number 7, sees that the number 7 is not divisible by 2 and it's bigger than 9, so it passes it on to active prime 3. Active prime 3 sees, oh, you're not divisible by 3. Oh, and you're smaller than 9, so you're a new active prime, so I'll create you. And active prime 3 gets connected to the last prime, which is 5, and it then starts to get, and so on and so on. So this is a version of the sieve of Eratosthenes for generating prime numbers, and it's implemented purely in terms of active agents, each of which is representing a prime number. They're connected in a data flow stage, a pole-based stage, and they work in parallel, so that at any point in time, at different points in the stage, in principle, there could be multiple tests for prime numbers happening at the same time. Each active prime is using a one-slot buffer in our implementation to feed values to the next active prime. So we could make the buffers longer, but as we've seen, whether we have a large buffer or a small buffer, the buffers will tend to either be empty or full. And in this case, as you can see, they tend to be empty. So the first active prime holds the seed value 2, gets values from test for prime, and creates new active prime instances whenever it detects a prime value. Here's the main class, the prime sieve class. It creates the initial configuration. So the first prime is going to be an active prime for 2, and it's connected to the test for prime instance. The interface between the objects is a source interface for some value, and it's quite simple. There's just a get operation which returns a value. Test for prime implements sources for integers, and the implementation is dead trivial. It simply keeps incrementing the next value by 1 until it reaches the max value which has been defined. An active prime also implements a source of integer, but it's also a thread, so it extends thread. There's a static variable, which is the last prime in the series. So when we add a new prime, it has to be connected to the last prime. This is a static variable, so it's shared amongst all instances of the active prime class. Every active prime holds a value, a prime value, and it remembers what its square is, so it doesn't have to recompute it every time. It knows what source it's connected to, where it's going to get the next value to test, and it has a one-slot buffer where it can put the values that should further be tested by the next prime in the flow. Here's our constructor. The constructor knows what value we are holding, what is our active prime value that we're testing against, and it also knows which integer source it's connected to, where it's going to get the values to test. Here's our run method. We first are going to try and get a value to test from our integer source, and that might block. Then we have the classical implementation of the sieve of Eratosthenes. If our test value is less than a square, then we've discovered an active prime, and we'll connect it to the last prime in the series. We will also use the test value set to 0 to inform all of the primes that they need to stop. If the test value is divisible by our value, then we throw it away. Otherwise, we push it, if it's not divisible, into our one slot buffer, so the next prime in the flow series will pick it up. So here in IntelliJ is our active prime class, which implements the integer source interface and extends thread. And here is our run method, which will grab an integer to test from the data flow chain, and if it finds one, will create a new active prime. And if it's unsure if the value should further be tested, it will put it into its slot for the next active prime in the series to test. Here's a demo, which is going to look for the first, for all the primes up to 10,000. And in case you had any doubt, here's the result when we run it. In this last section of today's lecture, we're going to look at Blackboard architectures. This is a very nice kind of a conceptual framework, and which has been implemented in a variety of so-called coordination media or coordination languages to support particularly data flow style architectures. So Blackboard architecture, instead of using one slot buffers that we saw in the previous example, they put all the synchronization in a so-called coordination medium or Blackboard, where agents can exchange messages. So what's different from what we just saw, with a fixed data flow stream, every process is connected to exactly one other process. So the communication flow is very strictly regulated. With the Blackboard architecture, it's a bit like having a bulletin board where you can post notes and you don't necessarily know who is going to pick them up. So think of a bulletin board at a supermarket where you can post information about your lost cat or the piano that you want to sell. So you post that information, and then other agents may look and discover these messages and take them and consume them, or copy information and even leave the message on the board. So agents do not exchange messages directly. So you do not address a message to a particular other agent, but you post a message which has a certain kind of a structure, and then other agents can retrieve these messages by using a kind of a pattern matching query. So you can encode, for example, in the message a location or a channel or an address or whatever, or other information. So the basis on which you find messages on the board, on the Blackboard, is completely open. In the work by Carriero and Galanter in their Lynda system, they describe how Blackboard architecture can be used to organize concurrent programs in a variety of different ways. One of these approaches is called result parallelism. So this is an architectural style based on blackboards in which we have workers who produce parts of a more complex whole. We see this visualized here. We have a bunch of workers here at the bottom, and each of these workers is posting partially completed work onto the Blackboard. Now we have another agent up here who's looking for these bits and pieces, and when it finds them, combines them to produce some other result. Now, of course, you can imagine that this tree can extend and become a multi-level tree. So you could organize these workers in a hierarchical way. So this agent, for example, can then put further messages here back on the Blackboard that other workers will pick up. A second style of parallelism that's supported by blackboards is so-called agenda parallelism. In this approach, it's not strictly hierarchical. We have a variety of workers which may perform different kinds of tasks. And what we find on the blackboard are not pieces of a whole to be created, but each message in this case is a task to be performed. Now we have various workers. Again, think of the pool of threads that you may have using JUC. So you have some fixed or floating number of worker threads, and these worker threads just look for tasks to perform. They pull the message out of the blackboard, and then in their work they may produce other tasks to be performed, which will then be picked up by other workers, and so on. So this is a less structured, so it's not strictly hierarchical, but leads to a kind of a self-regulating system. So as long as there's work to be done, workers will be picking up tasks. As long as there's new work to be done, workers will produce new tasks for the blackboard. Eventually the system acquiesces and we get our final result. So workers repeatedly retrieve tasks until everything is done. In this kind of a style, as opposed to the previous one where the workers are specialized to particular tasks, they produce particular parts of a solution. Here we have typically more general purpose workers who can perform any kind of task. So the information that's important is encoded in the message itself on the board rather than in the worker itself. And a third style that Carrier and Galanter speak about is so-called specialist parallelism. With specialist parallelism, every worker is specialized to perform a particular task. Notice, so here we have the yellow process, and it's interested in yellow tasks. It consumes yellow tasks and produces green tasks. The green process consumes the green tasks and produces pink tasks. Notice that this looks very much like a data flow. So whereas we had data flows as well in the previous ones, one a very hierarchical one, a second a very unstructured data flow, this one is more of a strict linear data flow. So very often these specialist designs are kind of equivalent to message passing organized as a flow architecture. Now Linda is the language and system that Carrier and Galanter implemented to support this style of programming. So on the one hand, you have a coordination medium, which is the blackboard itself. So that's a piece of software. And on the other hand is a language or a library, if you will, or a DSL, a domain-specific language, which is an extension of existing languages that provide you with primitives for accessing the blackboard. So Linda is on the one hand a coordination medium, and it's also a set of associated primitives for reading and writing messages to the blackboard. And these primitives can be added to existing programming languages. Over time, many different kinds of coordination media have been developed. Linda is one that supports a so-called tuple space. So the messages that sit in the blackboard can be basically seen as tuples, like relational tuples. And the tuples can contain data, so they're n tuples, and the tuples consist of primitive values, so typically numbers and strings. You can also have, as an extension to Linda, so-called active tuples. So an active tuple is an expression which can be evaluated, like a script or a fragment of a program, which once it's terminated produces a tuple that then is a plain old data tuple sitting in the coordination medium. So here's an overview of the Linda primitives. It's quite simple. This is all there is to it. First of all, we have out. Out takes as a parameter a tuple t. So for example, we can write out and then a bunch of values, strings, a mix of strings and numbers, for example. So we can say out employee Pingu 35,000. And this operation is non-blocking. So that means you can perform this at any time and it will immediately create a tuple in the tuple space. In addition to tuples, we have patterns, S. So an S is a query. It looks like a tuple, but it also has variables contained in it. So in S is a blocking operation that destructively reads a tuple from the tuple space if it matches the query S. So if we say in employee pingu $salary, that will match any tuple where the first value is the string employee, the second value is the string pingu, and the third element of the tuple is any value. So this will match in particular this tuple that's if it's been put in the tuple space, consume that tuple, and it will bind the variable salary to the value 35,000. Read is like in, but it's non-destructive. So it also blocks. It does exactly what in does, except it leaves the tuple in the tuple space. And in P is a non-blocking variant of in, which tries to input, but if it fails, if there's nothing that matches, then it will report that it failed. So it could raise an error, or it can return a Boolean false value. Read P is also the non-blocking version of read, so the non-destructive version. And finally, eval of E is an expression that represents a process that will execute, and when that process is finished, it should leave the result in the tuple space. So the effect in the end is like running the process and producing an out at the very end. So let's have a look at an example of a Fibonacci program implemented with Lynda, and we're going to use a variant of the tuple space implementation for Java called Java Spaces, and we're going to put a thin layer over the Java Spaces API so that it looks more like Lynda. So here's our implementation of Fibonacci using Java Spaces with a little bit of a Lynda-like layer in front of it. The idea is that Fib will compute the nth Fibonacci value and also leave in the tuple space a representation of that value, which is going to be available as a cache for further attempts to compute Fibonacci numbers. So the first thing we do is we try and read non-destructively from the tuple space. So we're looking for a tuple with three components. The first one says it's a Fibonacci number. The second one is n, that's saying this is the nth Fibonacci number. And the third value is the number that we're trying to find. So in this particular interface, since we don't have the question mark variable construct in Java, instead, if this succeeds, it will bind the tuple to the variable tuple here. And there when we look at it, we'll see we have fib, n, and the number which is not null. So this null here stands for wildcard. Say, please match anything that you find there. If this succeeds, then we're done. So if the tuple is not null, then we're done. If the tuple is null, that means, oh, we have some work to do. So this is actually the post condition that that big integer should ensure for us. It should ensure at the end that there is a Fibonacci tuple for the nth Fibonacci value in the tuple space. So that this should, when we do a read P, it should not return null, but should return the actual tuple with the value in it. So if that's true, we immediately return the result and we're done. So notice this is implementing kind of a cache for Fibonacci values. If, on the other hand, tuple returns null, that means there is no such tuple yet, well, then we have to do some work. First, let's see, this is going to be a recursive algorithm, so let's look at our base case. If n is less than 2, well, then we know what we have to do. Let's create a Fibonacci value with for n equals 0 or 1 with the value big integer 1. So this is non-blocking, and we're done, and we will immediately return this value. So that's the result of, that's the big integer value of Fibonacci. If we're not at the base case, now we perform the recursive version. So the recursive version here is an eval. So eval is going to do an out for us, but it contains a process. So the eval is going to produce Fibonacci of n, and it's going to compute. It's going to run this bit of code here, which is an eval, and it's going to return the Fibonacci of n-1 and Fibonacci of n-2. So it's going to find those two and add them and return that. Notice that this value was going to be computed is also going to be output to the tuple space. Now, once this is done, the tuple space has been populated now with the Fibonacci value that we wanted. So now this guy is going to succeed. It's a blocking operator. Here, before we did a read p, now we do a read. So this read will actually grab that value, and now we can return the tuple result. Of course, we had the tuple result. We could have optimized this code, but this illustrates quite clearly. Now the tuple is in the tuple space. We can grab it and return the final result. So there's the recursive algorithm implemented using Java spaces. Note that we've written the code in a very inefficient way because it's multiply recursive. However, since all the Fibonacci values are cached, we'll never actually compute the same Fibonacci value twice. After the first time it's being computed, the second time we will find the cached value and return it. So this is actually going to be a very efficient and linear algorithm. Now, I said that I added a very thin layer around the Java Spaces implementation because the Java Spaces API looks a bit different from what Carrier and Galanter did in Lynda. So just to show you, readp is implemented using tuplespace.read and so on. And inp is tuplespace.take, and out uses tuplespace.write. And eval is going to start a new thread which will run and eventually perform an out of the value of the expression that we computed. When we run this implementation, this is what happens step by step. And here we'll just use a small number of Fibonacci numbers so that we can see what's happening. First, we would like to compute the fifth Fibonacci number. So we do a read for the fifth Fibonacci, find that there's nothing there. So we have to evaluate Fibonacci of 4 plus Fibonacci of 3. And then we will try and, so this spawns a new process, and then we'll try and read from the tuple space the value that will be created, but that's going to block. Now to compute Fibonacci of 4 and Fibonacci of 3, we'll start by computing Fibonacci of 4. That, of course, returns null, so we'll have to evaluate Fibonacci of 3 plus 2. So Fibonacci 4 is going to block as well. We will next try and compute Fibonacci of 3. That's this one up here. And that results in Fibonacci 2 plus Fibonacci 1 being computed. That's going to block. Fibonacci 2 needs Fibonacci 1 and 0. That's going to block. Fibonacci 1, we know how to do that, so we're going to create the tuple directly in the tuple space. Fibonacci 0, we know what that is, so we'll produce that in the tuple space too. Now, as a result, the computation of Fibonacci 2, that process will terminate and produce as an output in the tuple space the Fibonacci of 2. And now reading that tuple will succeed and return. Similarly, we have a pending Fibonacci of 1, so the second one, which will also return. And now we can finally produce as an output the Fibonacci of 3, that returns, and so on down the line. And then very quickly we get to our final result, and we have the fifth Fibonacci value, which is going to be 8. So notice that despite the multiple recursion, because all of these values are cached in the tuple space, the result is quickly returned. We'll have a quick look at a demo of this actually running in Java. So our implementation is using a version of Java Spaces called Fly Java. In order to use it, we need to start the Fly server. So this is a simple command script that will run the Fly server. And here we see in our activity monitor that if we search for Fly, there it is running. Let's switch to IntelliJ. Here's our fib demo class, the one that we saw before. And here's the implementation of the fib algorithm. As you may recall, we first check if there's already a tuple in the tuple space matching the integer n that we want to compute Fibonacci for. If there isn't, if there is, we return it. If there isn't, we check if n is less than 2, then we immediately put the Fibonacci of 1 and 2 into the tuple space. And if it's bigger, then we compute Fibonacci of n-1 and n-2 in a new process that will end up putting the result into the tuple space. While that's running, we immediately block on reading that tuple. So when that tuple becomes available, when the eval has completed, then we'll pick up the result and we'll return it. Now, just like in the slide, we'll ask to compute the first 5 Fibonacci numbers. And if we run that, a little bit slow starting up on this machine. But it runs quite quickly once it's fired up. Well, maybe that's not so impressive. Since we can manage big integers, let's compute the first 100 Fibonacci numbers and see what that looks like. Notice that in our tuple space, we already have the first 5 Fibonacci values computed. So they will return quite quickly. There they go. But the others are also quite quick. So we're all waiting for the Fibonacci all the way up to Fibonacci 100, but they zoom right along there. And not bad for big integers in Java. Okay, that concludes the lecture for today. Thanks very much for your attention.